Today we're going to take a look at a different way to think about bandwidth. What really is bandwidth and what does it mean for your systems? Hi, I'm Daniel Bogdanoff, and today we're going to dig into arguably the most fundamental of all test gear specs, bandwidth. In Test Gear 101, you hear that bandwidth is simply the highest frequency component that you can measure or produce. For example, a 100 MHz oscilloscope can measure a 100 MHz sine wave. But this signal is going to be attenuated by 3 dB or so because in Test Gear 201, you hear that the signal will actually roll off a bit near the maximum bandwidth of your system. In fact, you can actually see frequencies that exceed the bandwidth of your scope. For example, here's a 40 MHz 5-volt peak-to-peak sine wave piped into my 1.5 GHz oscilloscope. No problem. But then I turn on my scope's 20 MHz bandwidth limit, and this is going to limit my bandwidth to just 20 MHz, down from 1.5 GHz. I can still see that 40 MHz sine wave, but the peak-to-peak voltage is attenuated down to just around 2 volts. So essentially, I'm able to see a signal that's double the effective bandwidth of my scope. The same will be true for the output of a function generator, but it's harder to see that in practice because the function generator software won't actually let you set a higher frequency than the generator's stated max output. On a 100 MHz generator, you simply cannot turn the frequency setting any higher than 100 MHz. So this begs the question, why don't we, the designers of test and measurement gear, simply say the generator can produce a higher frequency and then just limit the amplitude at those extended frequencies? Or why can't I say my oscilloscope actually has a higher bandwidth? Here I am able to measure double the bandwidth on this scope. It would certainly make our specs look better. To answer that, we need to look more closely at what bandwidth really means. As it turns out, it's not just about the hertz or the cycles per second, it's about the rise time. It's about how fast the signal goes up and down, edge speed. Let's look at an example. A delivery driver has a delivery truck that can travel 100 kilometers per hour. And let's say he has to make a delivery that's 50 kilometers away. It's going to take him 1 hour to deliver the package and get back. That's 1 delivery per hour. That's his frequency, his hertz. Next, he has to deliver 2 packages that are only 25 kilometers away. It only is going to take him 30 minutes for each package. His new frequency is 2 deliveries per hour. His frequency doubled, but his speed didn't really change. This is also true with test gear and bandwidth. An oscilloscope's bandwidth or generator's output is like the delivery rate, the deliveries per second, while the rise time is like the driver's speed. Sure, it can deliver more packages if the deliveries are closer together, but the travel speed doesn't change. This is the same with test gear. If I have a super high frequency input into my oscilloscope, and let's say this exceeds the bandwidth of my oscilloscope, what's going to happen is as this signal is rising, my oscilloscope is going to try to rise, and it's not going to be able to go quite as fast. And as soon as that signal starts to fall, it's going to go down, go up, down, up, down. So essentially I'm going to end up with the same frequency as my original signal, but the peak-to-peak voltage is not going to be as large. My delivery driver is not going to be able to drive as far, even though my cycles per second are the same. Another way to think about this is in terms of frequency components. Bandwidth refers to the frequency components when you look at the frequency domain, but the rise time or edge speed when you're looking at the time domain. I'm going to zoom in a little bit on the signal and watch my edge speed change as I toggle on and off the bandwidth. To see this even more clearly, I'm going to crank up my input to 60 MHz, and we can really see a difference in rise time between the two signals. So here's what's happening. As my signal increases, my scope tries to increase, but with that 20 MHz bandwidth limit on it, it cannot quite get there fast enough, and it can't just magically jump up to the new voltage value. The speed that the scope adjusts to the change is dictated by its bandwidth. So you can technically measure a frequency that's higher than the max bandwidth of the scope, but you cannot measure an edge speed faster than the max bandwidth of the scope. The same is true for a function generator. The edge speed of the output maxes out at its max bandwidth. That's why a 100 MHz function generator can create a 100 MHz sine wave, but not a 100 MHz square wave. The hertz is the same, but the edge speeds are very, very different. So if you're picking out a function generator, think about what types of signals you want to generate, not just the max bandwidth. A general rule of thumb for square waves is that you need a generator with at least 3 times the max bandwidth of your square wave frequency. You can also use this knowledge to push some of the specs of your scope, which is a topic for an upcoming video. But if you don't want to wait for that video, there's a blog version, there's a link for that in the video description. Thanks for watching. Make sure to subscribe to this channel, like this video, and let me know your thoughts in the comments. Bye.